Electrospinning of polymers, principles, materials, processing, and technological advances. Electrospinning is a versatile electrohydrodynamic technique widely employed for the fabrication of continuous micro and nanofibers from polymer solutions or melts. Owing to its simplicity, scalability, and ability to produce fibers with high surface area-to-volume ratios and tunable architectures, electrospinning has emerged as a cornerstone technology in materials science, biomedical engineering, energy storage, filtration, and advanced textiles. This video presents a comprehensive account of the historical development, fundamental principles, instrumentation, electrospinning methodologies, solvent and material selection, and the processing parameters governing fiber formation. Historical development. Electrospinning is rooted in early investigations of electrostatic phenomena in fluids, with origins tracing back to the 18th century when Abbé Nollet first observed electrically induced dispersion of liquids. Subsequent work by Zeleny in the early 20th century clarified the behavior of charged droplets under electric fields, establishing a scientific foundation for later developments. The first formal description of electrically driven fiber formation was patented by Anton Formhals in 1934, marking a pivotal milestone in the evolution of electrospinning technology. A critical theoretical contribution was made by Geoffrey Taylor in the 1960s, who mathematically described the equilibrium configuration of a charged liquid droplet, now known as the Taylor cone, characterized by a half-angle of approximately 49.3 degrees. Despite these advances, the technique remained relatively underexplored until the resurgence of interest in nanotechnology in the 1990s. During this period, Renneker and Rutledge systematically investigated the process parameters governing fiber formation and demonstrated the capability to produce nanometer-scale fibers. The advent of advanced characterization techniques, particularly scanning electron microscopy, further enabled detailed analysis of fiber morphology and accelerated the expansion of electrospinning research in the 21st century. Fundamental principles of electrospinning. Electrospinning is governed by electrohydrodynamic principles in which electrostatic forces overcome the surface tension of a polymer solution or melt. In a typical process, a polymer solution is introduced through a spinneret and subjected to a high-voltage electric field established between the spinneret and a collector. As the electric field intensifies, charges accumulate at the surface of the liquid, deforming it into a conical structure known as the Taylor cone. When the electrostatic repulsion exceeds the surface tension, a charged liquid jet is ejected from the apex of the cone. During its travel toward the collector, the jet undergoes elongation and thinning driven by electrostatic repulsion and bending instabilities. Concurrently, solvent evaporation or melt solidification occurs, resulting in the formation of continuous fibers with diameters ranging from tens of nanometers to several micrometers. The resulting fibrous assemblies exhibit high porosity, large surface area, and tunable microstructures, which are critical attributes for applications in filtration, biomedical engineering, and energy devices. Electrospinning techniques and methodologies. Electrospinning methodologies have evolved significantly, enabling precise control over fiber morphology and internal structure. The conventional needle-based approach remains the most widely used technique, wherein a polymer solution is delivered through a capillary needle. This method has been expanded to include coaxial and multi-axial configurations, which allow the fabrication of complex fibers such as core shell and multi-layered structures. These architectures are particularly valuable in applications involving encapsulation of bioactive agents, controlled drug delivery, and multifunctional materials. To address limitations in production rate and scalability, Needleless electrospinning techniques have been developed. These systems utilize alternative geometries such as rotating drums, discs, wires, or free liquid surfaces to generate multiple jets simultaneously. As a result, they offer significantly higher throughput and are more suitable for industrial-scale manufacturing. Additional advancements include gas-assisted electrospinning, which enhances solvent evaporation and jet stability, as well as centrifugal and high-speed electrospinning techniques that combine mechanical forces with electrostatic effects. Emerging approaches such as near-field electrospinning enable precise deposition of fibers with micrometer-scale spatial control, while three-dimensional electrospinning techniques facilitate the fabrication of structured scaffolds. Melt electrospinning represents another important development, eliminating the need for solvents, but requiring elevated processing temperatures. These innovations collectively broaden the scope of electrospinning and enable the design of increasingly sophisticated materials. Equipment and instrumentation. The electrospinning process relies on a relatively simple yet highly adaptable set of components. At its core, the system comprises a feeding mechanism, a high-voltage power supply, a spinneret, and a collector. The feeding system, typically a syringe pump or pressurized reservoir, ensures controlled delivery of the polymer solution at a constant flow rate. Syringe-based systems are commonly employed in laboratory settings due to their precision, whereas pressurized systems are more suitable for large-scale or continuous operations. The high-voltage power supply generates the electric field required to initiate and sustain the spinning process, with typical operating voltages ranging from several kilovolts to tens of kilovolts. The spinneret, often a metallic capillary, serves as the site of Taylor cone formation and jet initiation. Variations in spinneret design, including multi-needle and needleless configurations, enable control over production rate and fiber architecture. The collector plays a crucial role in determining the final morphology and orientation of the fibers. Stationary collectors, such as flat plates, produce randomly oriented non-woven mats, while rotating collectors, including drums and discs, can induce alignment by applying mechanical drawing forces. Specialized collectors, such as mandrels, enable the fabrication of tubular structures, whereas roll-to-roll systems facilitate continuous production. Processing parameters. The morphology and quality of electrospun fibers are governed by a complex interplay of solution properties, operational conditions, and environmental factors. Solution properties such as polymer concentration, molecular weight, viscosity, surface tension, and electrical conductivity are critical in determining the stability of the jet and the formation of continuous fibers. Adequate chain entanglement, typically achieved through appropriate polymer concentration and molecular weight, is essential to prevent bead formation and ensure uniform fiber morphology. Operational parameters, including applied voltage, flow rate, and the distance between the spinneret and collector, directly influence the electrostatic forces and jet dynamics. Increasing the applied voltage generally enhances jet stretching, although excessive voltage may lead to instability. Similarly, the flow rate must be carefully optimized to maintain a stable Taylor cone, as excessive flow can result in bead defects and incomplete solvent evaporation. The spinneret to collector distance determines the flight time of the jet and must be sufficient to allow complete solvent removal before deposition. Environmental conditions such as temperature, relative humidity, and airflow also play significant roles. Temperature affects solution viscosity and evaporation rate, while humidity can influence pore formation and fiber surface morphology. Controlled airflow within the electrospinning chamber can enhance solvent removal and improve process stability. Solvent selection. The selection of an appropriate solvent system is a critical determinant of electrospinability and fiber quality. The solvent must effectively dissolve the polymer, provide suitable viscosity and conductivity, and evaporate rapidly during jet travel. The physicochemical compatibility between polymer and solvent is often assessed using Hansen solubility parameters, which account for dispersion, polar, and hydrogen bonding interactions. Commonly employed solvents include halogenated solvents such as chloroform and trifluoroethanol, aprotic solvents such as dimethylformamide and dimethylacetamide, and protic solvents such as ethanol and water. In many cases, mixed solvent systems are utilized to balance solubility, volatility, and electrical conductivity. For instance, combining a high-volatility solvent with a more conductive, less volatile solvent can improve jet stability and fiber uniformity. In recent years, increasing emphasis has been placed on the development of environmentally benign solvent systems. Regulatory frameworks and sustainability considerations have driven efforts to replace hazardous solvents with greener alternatives, including water-based systems and bio-derived solvents such as ethyl lactate. These developments are particularly important for large-scale manufacturing and biomedical applications. Polymer and material selection. The versatility of electrospinning arises largely from the wide range of materials that can be processed into fibers. Organic polymers constitute the primary class of materials used in electrospinning, encompassing natural, synthetic, and semi-synthetic polymers. Synthetic polymers such as polycaprolactone, polylactic acid, and polyvinyl alcohol are widely employed due to their tunable mechanical properties and ease of processing. Natural polymers, including collagen, gelatin, chitosan, and silk fibroin, are particularly attractive for biomedical applications owing to their inherent biocompatibility and biodegradability. The selection of polymer is fundamentally dictated by the intended application, as it determines the mechanical strength, degradation behavior, and functional properties of the resulting fibers. In many cases, polymer blends or copolymers are employed to achieve synergistic properties. Conductive polymers, such as polyaniline and polypyrrole, present additional opportunities for applications in electronics and sensing. Although their inherent brittleness and poor processability often necessitate blending with carrier polymers. Beyond conventional polymers, composite and hybrid materials incorporating nanoparticles, ceramics, or metals have been extensively explored. These materials enable the integration of functionalities such as electrical conductivity, catalytic activity, and enhanced mechanical performance. Additionally, small molecules can be electrospun under specific conditions, particularly when self-assembly or carrier polymers provide sufficient chain entanglement. Applications of electrospun fibers. Electrospun fibers possess unique structural and functional characteristics that have enabled their widespread adoption across diverse fields. In biomedical engineering, they are used for tissue scaffolding, wound healing, and drug delivery, where their high surface area and controllable porosity facilitate cell attachment and controlled release. In filtration, electrospun membranes provide superior efficiency in capturing fine particles due to their small fiber diameters and interconnected pore structures. In the energy sector, electrospun materials have been utilized in batteries, supercapacitors, and fuel cells, where their high surface area enhances electrochemical performance. Additional applications include sensors, flexible electronics, smart textiles, and packaging materials. The transition from laboratory research to industrial implementation has been supported by advancements in scalable manufacturing techniques and adherence to regulatory standards for medical and commercial products. Conclusions and future perspectives. Electrospinning has evolved into a mature and highly adaptable platform for the fabrication of nanostructured fibrous materials. Its ability to process a wide range of polymers and composites into controlled architectures makes it uniquely suited for next-generation applications in healthcare, energy, and environmental technologies. Future developments are expected to focus on improving scalability, enhancing process control, and advancing sustainable practices through the use of green solvents and energy-efficient systems. Continued interdisciplinary research will further expand the capabilities of electrospinning and solidify its role as a key technology in advanced materials science.